Good morning, everyone. My lesson today is a little bit longer, so I'm not going to wait too long for people to join. I'm going to wait about 1 minute and then I'm going to start. All right, I think I'm going to start. So I'll just begin with a review of what we discussed last time. So last time we learned about what a force is. And a force is a push or pull, essentially. Okay? The units of force are called newtons, N. And so once I defined what a force is, or what a force does, we then talked about Newton's 3 laws of motion. So the first law of motion was the one that said objects in motion stay in motion, objects at rest stay at rest. So we learned a more mathematical way of stating that, and the mathematical way of stating that is that the acceleration is 0 when the net force is 0. Okay, so if there's no net force, then the acceleration is going to be 0. Acceleration being 0 is another way of saying that the velocity is not changing. The velocity is a constant. Okay? And we talked about the converse of this, where you have, the converse of that doesn't make any sense whatsoever. The second law of motion is the most important equation in the course. We're going to use it repeatedly, starting from now. And it says that the net force equals mass times acceleration. Okay, the net force, if you remember, is the total force. Okay, so if you have a bunch of individual forces acting on an object, the net force is the combined result of all of those. And then the third law of motion says for every action, there's an equal and opposite reaction. And so the mathematical statement of that is that the force that Bob exerts on Alice, and Bob and Alice, I'm just saying that because it's just two objects. The thing that object B exerts on object A is equal to minus the force that Alice exerts on Bob. So these are equal and opposite. So that is what we learned last time. Today, what we are going to learn about are some different types of forces. So what are the specific forces? We just talked about, we talked about forces in general, but we haven't talked about specific forces. So let me go over some different forces in this class. The first type of force that you might encounter is what's called an applied force, which I will denote by F sub A. Hurts to be left-handed. Look at that. Just wiped it all. Applied force. So an applied force is basically an unspecified force. Okay, it might be the force from a human pushing or pulling on something. It might be a force from a machine pushing or pulling on something, but it's just an unspecified force we refer to as an applied force. Okay, a force is applied on an object. So that's the first type of force. That one requires sort of no explanation. It's just a random force. The other force, the next force we will talk about, is called the weight force. And the weight force is the force due to gravity. So gravity is pulling all of us downward. It's the force that's called the weight force. You could also call it the gravitational force if you wanted to. So the force due to gravity, it points downward. Towards the center of the earth. Okay. So I'm going to give you a formula for weight force. The weight force is mass times gravity. Mass times gravity is the weight force. So, for example, if you have a 50 kilogram person, that's the mass of the person. So their weight is going to be 50 kilograms times 10 meters per second squared equals 500 newtons. That's the gravitational force acting on the person. Now, one of the things about the weight force is that it can vary from place to place. Okay? It can vary from place to place. So, for example, if I take you and I move you to Mars, if I take you and I transport you to Mars, you have the same mass here as you do on Mars, because the mass measures the amount of matter that is inside you, okay? But when I transport you from the Earth to Mars, I took you from a gravity that is 10 meters per second squared to a gravity that is about the yawns. To a gravity that is only 3.7 meters per second squared. So even though your mass didn't change, your weight did change. Okay? So mass and weight are two different things. Mass is a property of you. Your weight is a property of you at a certain location. Okay? Because the G value changes from place to place. Okay? So if you go to the moon, G is only 1.6 meters per second squared. So you're going to weigh less on the moon, even though you're the same person with the same mass. Okay? So that is the weight force. The next force I want to talk about is called the normal force. The normal force is the force from a surface that keeps objects from passing through. Okay? If I take a cup and I set it on the table, gravity, the weight force, is pushing the cup downward. Okay? So if there was no normal force, the cup would pass through the floor and accelerate down. Okay? So we need a normal force in order to allow us to set one object on top of another object, for example, or to, if there was no normal force, if I push the cup against my hand, the cup would just pass through my hand, okay? So the normal force kind of keeps objects from passing through each other, okay? It is denoted by F sub n for normal, force of normal. And the normal force points perpendicular to the surface, perpendicular and away from the surface. Okay? So, for example, if I have a table, like my desk here, the normal force points upward, away from the table. Okay? If we look at the ceiling, the normal force points down, away from the ceiling. Okay? If you have a wall, like the wall behind me, the normal force is going to point towards you guys, away from the wall. All right? So it always points perpendicular to the surface and away from it. So we're going to do a number of examples with normal force because it can be a little bit tricky. Paper. So here's a very simple example. Okay. So what if you have a floor like this, and you have a person standing on the floor? Okay. And that person has a mass of 60 kilograms. Okay. What is the normal force acting on the person in this case? Well, we're going to draw what's called a free body diagram. So a free body diagram is a picture of the forces that are acting on an object. So I'm going to represent the object experiencing the forces as a dot. So this dot is the same thing as that person. Now, this person is experiencing a gravitational force pulling it downward. Okay? So the gravitational force is going to be mg. So 60 times 10 is 600 newtons. The normal force points away from the surface, so that points upward, F sub n. Now it turns out that the normal force has to equal the weight force in this case. In size. They're in opposite directions, but they're the same size. So in this case, the normal force would be equal to 600 newtons. And to understand why, we just have to think about the converse. What if the normal force was not equal to 600 newtons? So, for example, what if the normal force was 650 newtons? And the weight force is only 600 newtons. Then that means you would have a net force of 650 up and 600 down. That's a net force of 50 newtons. And if this person has a net force of 50 newtons, then they would accelerate up into the air, which is ridiculous. They're just standing on the surface. They're not flying through the air, okay? So that doesn't make sense. What if you had the weight force is larger than the normal force? What if the normal force was only 300 newtons and the weight force is still 600? Then you would have a net force of negative 300 newtons, downward 300 newtons. That doesn't make any sense because it would be like you're standing on the floor, but you're accelerating downward through the floor. So that can't be the case. The only sensible option here is that the normal force equals weight because the person isn't accelerating up or down. Okay? So what you'll find is that often, not always, but often, the normal force is equal in size to the weight force. Not always. We're going to do 3 examples now where the normal force is not equal to the weight force. Okay? So here's some examples. What if you have that same you have that same 60 kilogram person, okay, but that person is being pushed downward by an additional 100 Newton applied force. Okay, what's the normal force here? Well, the normal force points upward. Its size, we're going to determine it. But there are 2 downward forces. There's a 600 Newton downward weight force. That comes from M times G. And then there's an additional 100 Newton downward force. So the total amount of downward force is 700 Newtons. So that means the normal force has to equal 700 Newtons. Why? Because if the normal force was less than 700 Newtons, there would be more downward force than upward force, and the person would pass through the floor. Okay? So the normal force is basically whatever value it has to have in order to keep the thing from passing through the surface. Okay? Let's do another example. What if you have a wall and that wall has a 5 kilogram block? Okay, and the 5 kilogram block is pinned to the wall by a 100 Newton applied force. So what does the free body diagram look like in this case? Well, you have the weight force going downward. Weight force always goes downward. That would be 50 newtons. mg, 5 kilograms times 10 meters per second squared. Okay. You have the 100 Newton applied force. Okay. And the normal force in this case is going to point to the left, perpendicular to the surface, away from it. So F sub n. All right. I see there's a really good question in the chat, and I will get to it in a second. So in this case, the 50 newtons plays no role in the normal force. A wall doesn't care if you slide up and down along the wall. Okay? What the wall cares about is that you don't pass through it. So it's only the force that is pushing it into the wall that needs to be countered, okay? So that means that the normal force in this case would be 100 newtons. These two forces have to be the same. It doesn't matter what the weight force is in this case, because the weight force isn't pushing the block against the wall. It's the 100 Newton force that pushes it against the wall. So you could have a 1,000,000 kilogram object that's being pushed by 100 newtons into the wall, and the normal force is only going to be 100 newtons. Okay? I hope that makes sense. I can't stop yawning. So there is a really good question in the chat, which is, what if the surface is glass or another fragile surface? We could think about the strength of the surface as equal to the maximum normal force it can apply without breaking. So a really strong surface can exert a really big normal force before it collapses. So you can think about there being different surfaces have different maximum normal forces that they can apply. Okay? A glass window, for example, is going to have a relatively small normal force that it can provide before it shatters. So I hope that answers your question. Do one more example here. Notice how these are examples where normal force is not equal to the weight force. What if we have a person in an elevator? Okay. And it's this 60 kilogram person. The elevator is accelerating upward at 3 meters per second squared. So if you are in an elevator that is accelerating upward, you are also accelerating upward because you are in the elevator, right? You also have an upward acceleration of 3 meters per second squared. So if we draw the free body diagram for this person, they have the normal force from the floor of the elevator, okay, and then they have the 600 Newton weight force going downward. But as I've drawn it here, the normal force is bigger than the weight force in this case. Because if it wasn't, then so in order for the person in the elevator to accelerate upward, there has to be more upward force than downward force. You get what I'm saying? If there was an equal amount of upward force and downward force, then it would just be at rest. But in order for the elevator to accelerate upward, you need more upward force than downward force. So how can we calculate it? Well, we could use Newton's second law. Net force equals ma. So the net force is going to be the upward force minus the downward force. Or if the thing was moving horizontally, it would be the rightward force minus the left force. So we have up minus down. That's going to be F sub n minus 600. And that equals the mass of the person, which is 60, times the acceleration of the person. The acceleration of the person is 3 meters per second squared because they are in the elevator, accelerating with the elevator. So solving this equation gives a normal force of 600 plus 180, so that is 780 newtons is the normal force. Okay? So I've given you 3 examples where normal force is not equal to weight force. All right. The next force I want to talk about is called the frictional force. Friction. Okay. What do you need to know about friction? Friction is a force that resists surfaces that slide across each other. Okay? Friction is an oppositional force. So what does that mean to have an oppositional force? It means that if you are pulling something to the right, then friction is always going to oppose that motion. So it's going to friction is going to fight back to the left. So it always opposes what you're trying to do. Okay. There are two types of friction. There is something called kinetic friction, and there is something called static friction. So these words are the keys to what they are. By the way, friction in general is denoted by a curly F. So kinetic means motion. So kinetic is the friction while the object is sliding. Okay, so if I have a cup of coffee and I push on the coaster and it's sliding, I am fighting against kinetic friction while it is sliding. Okay, I'm fighting against kinetic friction. We could think about kinetic friction. It's the force that must be overcome to keep an object sliding. You have to continually apply at least the kinetic friction force. So you have to at least overcome kinetic friction in order to keep an object moving. So for example, if kinetic friction was 10 newtons and you applied 10 newtons, then the object is going to keep sliding at a constant speed. If you applied 11 newtons and kinetic friction is 10 newtons, then you're applying more than enough to keep it sliding, so it's actually going to accelerate. Okay. If it's sliding and kinetic friction is 10 newtons and you apply 9 newtons, you are not applying enough force to overcome friction, so the object is going to slow to a stop. Okay. Static friction, so static means not moving, unchanging. Kinetic means motion. So static friction is friction before sliding. Okay, so what if I'm applying a force? So I'm applying a force on the coaster right now, but the coaster is not moving. That is because I have not overcome static friction. Okay, so there is friction. There is a force fighting back against my push, and that is called static friction. If I push hard enough that it starts to slide, now I have kinetic friction. But if I'm not applying enough to slide it, I'm fighting against static friction. Okay? So you could think about static friction as the force that must be overcome to make an object budge. You guys know what budge means, right? Budge means to start to move, that initial jump that something has when it starts to move. Okay? So there's a formula for friction. I'm going to give you the friction formulas at this time. The formula for kinetic friction. So kinetic friction is denoted by F sub K, is mu sub K times the normal force. So the first thing I want to notice is that the kinetic friction force is proportional to the normal force. So what that means is that the more normal force you have, the more friction you have. Okay? This is really easy to test out. If you have your hands and you push them together lightly, so very lightly pushing them together, it's really easy to slide them across each other. But what if I apply some strength and I really push my hands against each other? Then it's much harder to slide them across each other. So the more two surfaces are pushed together, the more normal force they have, the more friction you're going to get. Mu sub K is called the coefficient of kinetic friction. And the coefficient of kinetic friction is a property of the surface itself. It's a property of the interface. Okay? I'm going to write that down. So, coefficient of kinetic friction is a property of the interface. So there's a certain coefficient of kinetic friction for skin to slide across skin. There's a certain coefficient of kinetic friction for tire on the road. Tire on pavement, that has a certain coefficient of friction. There's a certain coefficient of friction for metal on ice. So the more slippery the surface is, the smaller the coefficient of friction. Okay? There's a certain coefficient of friction of the sole of your shoe on the pavement as well. There's not really much of a way to calculate what that is. It's an experimental quantity. So the only way to know what the coefficient of friction is you put two things on the surface and you try to slide them across each other. So this is an important formula. All right. Static friction is a little bit trickier. So static friction is denoted by mu sub s. And the reason that static friction is tricky is that I can apply different amounts of force, okay, without the object moving. I can apply almost no force and be lazy and the object doesn't move. Or I could apply almost enough force to make it move, but it still doesn't. And static friction deals with all of those possibilities, okay? So the static friction the amount of static friction force depends on how hard you push. But one thing that's true is there is a maximum value for static friction. And that maximum value is S times normal. So mu sub S is predictably the coefficient of static friction. So there's a coefficient of static friction and there's a coefficient of kinetic friction. Generally speaking, kinetic friction is smaller than static friction. Have you ever been pushing something that's really heavy and you try to push it and maybe it doesn't budge. And then you ramp up your strength and you go, ooh, and it moves. And once you get it moving, you might find that once you get an object moving, it's easier to keep it moving. Okay? So generally speaking, it's harder to get something started than it is to keep it moving. And so the mathematical way of saying that is that the coefficient of kinetic friction is less than the coefficient of static friction. Okay. There's a question about what is this symbol here. So this is the Greek letter mu. Okay. It's kind of like a fancy M crossed with a fancy U. All right. So it kind of has a dangling front. It's a U with a dangling front, or you can think about it as an M. I don't care. Okay. So let's do an example with friction. So here's an example. We have a flat surface and this flat surface, there's another question in the chat. Is there a friction for stopping? So yes, good question. Thank you for asking. So if something is stopping, if you have something sliding to a stop, then that would be kinetic friction that is stopping it, because the thing that is resisting the object's motion is kinetic friction. Good question. So let's suppose that you have a 2 kilogram object on a surface, and again, the coefficients of friction are a property of the interface of what two things are against each other. So we'll just say that the coefficient of static friction is 0.8, and the coefficient of kinetic friction is 0.3. So as I said, usually it's tougher to get an object started moving than it is to keep it moving. So that means kinetic friction is smaller. So let's draw a free body diagram for this box. So I'm representing the box as a dot. Oh, and by the way, there's also an applied force pulling the box to the right. So we have this applied force. Now this applied force wants to move the box to the right. So friction is going to oppose it and exert a force to the left. So friction goes to the left. There are some other forces involved. There's also the weight force going downward. Okay. The weight force is going to be m, which is 2, times gravity, which is 10. So mg equals 20 newtons downward. And then we have an upward normal force. Now again, in this case, the normal force has to equal the weight force, because the box isn't jumping into the air and it's not getting crushed into the ground. So the only sensible thing is that these two forces should be equal to each other in size and in opposite direction. So the normal force is 20 newtons. So we know the normal force and we know the coefficients of friction. So that allows us to calculate the maximum static friction and it allows us to calculate the kinetic friction. Okay? So the maximum static friction is mu sub s times normal. Okay? So mu sub s is 0.8. The normal force is 20. So that means that the maximum static friction is 16 newtons. So this is the force required to budge. You need to apply at least 16 newtons to budge the object. Kinetic friction is mu sub k times normal. So that is going to be 0.3 times 20, which is 6 newtons. So that is the force required to keep it moving. So if the object is sliding and you're only applying 5 newtons, then it's going to slow to a stop eventually, okay? If it's sliding and you're applying 6 newtons, then you're applying just enough to keep it moving, so it's going to continue to slide at a constant speed. Okay. So let's do a couple of cases here. So what if the applied force is 10 newtons? What if the applied force is 10 newtons? And we're going to say the box starts at rest. So the box is at rest. Okay. If the box is at rest, is 10 newtons enough to make it start to move? Well, we need at least 16 newtons to make it move. So because 10 newtons is not enough, the box won't move. The box won't budge. Another way of saying the box won't budge is that the acceleration is 0. No acceleration of the box. Okay? One of the reasons that static friction is a little bit... so the box doesn't budge, so that means we have static friction. Okay? One of the reasons that static friction can be a little bit tricky is because the value that it has is sort of indefinite, okay? And actually in this case, static friction is equal to 10 newtons. And so you might be asking the question, well, why isn't static friction 16 newtons? Well, this is the maximum static friction. It doesn't mean that that's what friction will actually be. It's the maximum value that static friction can take. The way static friction works is that it matches the applied force. Okay? It matches the applied force okay, up to the maximum. So if you apply 5 newtons of force, then static friction is going to fight back with 5 newtons of force. If you apply 8 newtons of force, then static friction is going to fight back with 8 newtons of force. If you apply 15 newtons of force, then static friction is going to fight back with 15. So it kind of goes toe-to-toe with you up to the maximum value. Okay? The reason that static friction can't be 16, it would be absurd if static friction is 16 newtons in this case. That would be like you applied 10 newtons And what if static friction was 16 newtons? That would mean that there was a net force of -6 newtons, which would mean that the box would accelerate in the opposite direction. So can you imagine a world where you pull on an object and you're not strong enough to move it, and so it accelerates away from you? That doesn't make any sense. Okay, that's kind of ridiculous. So the way static friction works is it matches you up to the maximum. There's a good question in the chat, which is, what if you applied exactly 16 newtons? Yeah, if you applied exactly 16 newtons, static friction can go up to 16 newtons, so it wouldn't move. If you applied 16.000000001 newtons, then it would start to move. So yeah, you have to apply something greater than that amount. So now, let's redo the question. What if the applied force is 20 newtons? 20 newtons is greater than the maximum static friction. So what's going to happen is the box will budge. The box budges. And if the box budges, then now we have kinetic friction. Okay? And kinetic friction, it doesn't have any of this maximum value business. So if it's sliding, kinetic friction is 6 newtons. Okay? So if we think about this, we have an applied force of 20 newtons, which was enough to make it move. So now it's moving, and we get kinetic friction fighting back with 6 newtons of force. So what that means is that our net force is 20 to the right minus 6 to the left is 14 newtons. So we can get the net force, and we can actually calculate the acceleration using Newton's second law. Net force equals ma. The net force is 14 newtons. The mass is 2 kilograms. So we have 14 equals 2a, which means that the acceleration is 7 meters per second squared. 7 meters per second squared. Okay? So depending on what the applied force is, you get a different acceleration. I'm going to teach you about one more force, which is the so-called elastic force. And the elastic force is denoted by F sub E for elastic. And it is the force that resists stretching, compressing, bending, twisting, etc. So any material that can be deformed is going to resist that distortion. Okay? If I take a rubber band and I stretch it, the rubber band resists that distortion and tries to come back to where it was originally. If you have a mattress spring and you compress it, the mattress spring resists being compressed and tries to extend back to where it was. Okay? So this is the way the elastic force works. It is an oppositional force, just like friction. Okay, and so there is a nice formula for the elastic force. It is K times X. So K is called the stiffness. Okay, units of stiffness are newtons per meter, and it is a property of the thing that is being stretched or compressed or bent or whatever. Okay, so different springs, for example, have different stiffnesses. For example, there's a spring in your car. It's called the shocks, right? The shocks are very stiff. You can actually buy different shocks with different stiffnesses, but if you have shocks with a low stiffness, then your car is going to bounce a lot when you go over a bump. Okay. Different rubber bands have different stiffnesses. For example, if you get super thick rubber bands, then those are stiffer than thin rubber bands. The stiffness can also depend on how old the thing is, how many times it's been used. A good example of that is the elastic band in your underwear. If you wear the elastic bands, or you wear the underwear, I don't know how many times. I've never thought about that. How many times is a pair of underwear used before it is time to replace it? I don't know. But, you probably wear it dozens of times. Okay? And each time you wear it, you're stretching the rubber band, and it gets worn out over time. You put it in the washing machine. The hot water in the washing machine makes the stiffness of the elastic band go down as time goes on. So, it can depend on time as well. X is called the extension. And it is basically the amount stretched or compressed beyond its natural size. So, for example, what if I have and that's important, it's the amount beyond its natural size. What if I have a 10 centimeter long rubber band? Okay. And what if I hold the ends of the rubber band so that they are only 5 centimeters apart? Okay. In this case, the rubber band is not going to be taut. So the rubber band is going to, do something like this because there's extra length in the rubber band. And in this case, because I haven't gone beyond its natural size, we have x equals 0. There's no extension. What if I then pull the ends of the rubber band so that now the two ends are 10 centimeters apart? So I have pulled the rubber band taut, but I haven't actually stretched it yet. So still, we have x equals 0. But now what if I stretch the rubber band and I go beyond its natural length? Okay. It's beyond its natural length now. Like that. So that now the two ends are 17 centimeters apart. Well, in this case, I have gone 7 centimeters beyond 10. So I would say that x equals 7 centimeters. Let's do a really simple example. A scale. So what is a scale? A scale is basically a spring, okay, and then the spring is attached to some kind of a plate. This is one type of a scale, by the way. You could also have a balancing scale. So here's the plate that is being held up by the spring. And we put some stuff on the plate. So maybe we're at the grocery store and we put some oranges on there. Okay, so here's some oranges. Okay, now what if the scale has a stiffness of 110 newtons per meter? We then, okay, when you put the oranges on the scale, the oranges cause the scale to extend by 0.04 meters. What is the mass of the oranges? So this is how a scale works. Depending on the amount that it stretches, we can determine how much mass was put on it. Now, if we think about these oranges, they have the elastic force supporting them. It's the spring that is supporting them. And they have a weight force going down. And because the oranges are just sitting in the scale, those two forces have to balance. If they were not balanced, then the oranges would be accelerating up or down. So we have to have kx equals mg. Gravity is 10. The stiffness is 110. The x is 0.04. Okay, so that says 4.4 equals m times 10, which says that m equals 0.44 kilograms. So we determine the mass of the oranges by seeing how much the spring extended. Okay, so I accidentally went a little bit long today. I was kind of long-winded, I guess. The assignment for this is Forces Quiz 2. And so we're not going to have time to go to the Zoom room today. But if you have any questions on Forces Quiz 2, please come to see me during office hours from 1:40 to 2:30. And I'm more than happy to answer your questions, all right? I mean that. I enjoy answering your questions. I have one more thing to say, and I'm forgetting what it is. Make sure you fill out the attendance form, okay? Because I have no clue who is watching. I can see that there are 36 people watching, so I assume that means all of you. But if you don't fill out the form, I can't be sure. All right? Have a really nice day, and I hope to talk to you during office hours. Bye.